Hey there! Do you work with data? Does it look somewhat like this? And would you like to learn more about your data? Maybe find patterns or hidden information inside? What if I tell you that you can apply AI to do so? It is actually super easy. Give me a moment of your time and I will show you how you can be a data scientist too. My name is Abutita, and I'm your guide to learn all kinds of tricks and concepts about artificial intelligence and machine learning. My partner in crime today is called Linny. He wants to be an AI and asks us for our help. We will help him, of course. Today, we will teach him how some things in our world are connected. For example, more hot days in summer lead to more ice cream eating. In the end, we will be able to ask him for a simple number and he will be able to respond. So, if we taught him how many hot days there were in the last years and how much ice cream was sold, he will then be able to tell us how much ice cream we will eat next year if he knows the number of hot days. But what does this have to do with our neighbor's tiger who loves ice cream? Why is he in danger? We better hurry with the topic and find out. The topic today is the simplest algorithm in the field of machine learning. It is called linear regression. Apart from hot days and ice cream, there are some other very common use cases for this algorithm. It is frequently used in sales, in finances, in estimating housing prices. But for now, we stick with the ice cream because it is cuter. To understand better how it works, let's start with where the name is coming from. A regression is a technique from statistics. But do not worry, we will not delve too much into the maths. Just remember that a regression relates two variables to each other. So, for example, if more people watch this video, the world will have more data scientists. Changes in the first are related to changes in the second, and that is called a regression. Linear means that something is a straight line. It can go up, go down, or stay at the same height, but it is always straight. In a nutshell, linear regression means that we relate two variables to each other with a simple, straight line. And to do this, we need two things. Your data, of course, and a formula for the straight line called linear equation. Maybe you remember it from school. This linear equation consists of only 4 elements. And to make this easier to understand, I will demonstrate it with some axes. Voila! The first element is the independent variable x, which is your input, let's say, cats. Then we have the dependent variable y, which changes when your input changes, let's say, happiness. The slope m, that tells us how strongly y relates to x. So, how much happiness does each cat bring us? And our bias b, which defines where we start on our y-axis, our base happiness. And that is all we need to express any kind of straight line. Okay, enough maths for the moment. Let's look at some data. These colors get me every time. With this data, we can now feed our AI and let it learn how our input x, the cats, relates to our output y, our happiness. And as you see, it finds a linear equation that describes the relationship perfectly. With this equation, we can estimate y values if we put in new, not yet known x values. That is pretty useful in a lot of situations. But maybe now you want to intervene and say, well, that was easy. I could have done that with my bare eyes, right? And you are right. This example was easy enough to see the relationship with our own eyes. But as you might have guessed, that is often not the case. Let's look at a data set that is a bit less obvious to describe. This one is trickier, don't you think? And if we let the algorithm take a look again, it gets a pretty good grasp on how to describe the dataset with a linear equation. Okay, that was impressive, but how does it actually work? Let's watch the process together. Here, we see that with each new data point, the linear equation adapts to the new information and changes its bias and its slope. This goes on until it has seen so many data points that it hardly changes anymore, and this we call convergence. And just like that, we have a new linear equation to predict our y values for new x values. And if you now want to say, well, that looks handy, but unfortunately my data is not related linearly, give me a second. I want to present to you a special case called polynomial regression. Polynomial functions grow exponentially. That is what makes them differ from linear functions. We can now allow our linear regression to make use of this exponential nature if it may deem necessary. This means, with just a few alterations in our maths, we can now describe nonlinear data too. Look! Isn't that fascinating? We don't need a straight line anymore. This curvature is a special case of the linear regression. It is based on the so-called polynomial function, hence the name. We won't go into detail here, but if you're curious, I will put a link into the description. And that is still not all we can examine. Let me introduce you to the three-dimensional space. In the 3D space, our linear regression is a two-dimensional plane. Isn't that awesome? Imagine how much hidden information might hide in your data. You just have to take a thorough look at it. Okay, this is it for the possible variations for now. You remember we talked about Linny, right? Now, you hopefully see how we can teach him about data for him to make use of it. We show him as much data about hot days and the average amount of ice cream as we can find. And after he has seen enough data, we can again ask him about the future amount of ice cream. And he can predict it quite accurately. Unfortunately, when you use him, he probably won't be a cute robot. More likely, it will be a console on your computer or some website to enter data. But hopefully, this gives you an idea what happens behind the curtains. But wait, what was all that about our neighbor's tiger? You see, sometimes you find a connection between two things. But the connection is by chance. There's no real connection. Data scientists call that a correlation. Two things behave similarly but are not connected. If they are connected, that is called causation. That means when one changes, the other one will also change. They are intertwined. Our neighbor's tiger was originally at risk. He loves ice cream more than anything else. But there is a famous study that shows that more ice cream leads to more murder. Luckily, that is merely a correlation and our neighbor's tiger is not in danger. It seems that both things tend to happen more in summer instead of being connected. So, thanks to statistics, he is safe. Wow, you're still here and want more? Okay, let's dig deeper. There are some metrics we can consult to get a better idea of whether what we are doing makes sense. To make this clearer for you, look at this graph. You remember it, right? We used it to explain the first steps of linear regression. We will now adjust it a little bit to create something called residual plot. And the result looks like this. Magnificent, isn't it? With this plot, we can visually evaluate if our function fits our data well. Look at the distribution of the colorful dots. They are evenly distributed around the zero line. That means our function suits our data really well. And in case our function does not describe our data well, for example, if we use nonlinear data and try to describe it with a linear function, then the residual plot will look like this. Here, we see that the colorful dots are not distributed evenly around the zero line. That means the function does not describe our data well at all. And that is not just a vague feeling of ours. We can measure the quality of our fit with a metric called explained variance. The explained variance is called R² among experts. It calculates the distances between all the data points and our linear function. With this, it can measure how well the function describes the data. The ideal result would be 1, whereas the worst result would be 0. And here we see that our first model, the linear function on the linear data, performs far better than the linear function on the polynomial data. That means that our intuition did not fool us. So now we can argue with numbers if anyone asks us why we have chosen a specific model. And if one day we are not sure about our results, the R² metric may help us in evaluating what we should do. Maybe change the model. But that is a topic for another video. We call it a day at this point. If these concepts intrigued you, feel free to look them up. I will put some links and resources into the description. Just look for the keywords I mentioned. If you liked this video, I would be happy to see you subscribe. If not, that is fine too. See you next time. Bye.